Good day. My name is Natalia Kosheleva, and I am a scientific researcher in the Institute of Continuous Media Mechanics of Russian Academy of Science. I would like to present you a work titled Monitoring of Concrete Forming by Embedded Fiber Optic Sensors, which was done together with my colleague Grigory Serovaev and Georgy Gusev. One of the directions of research in the field of materials science is related to development and preparation of smart materials. According to the classification of smart materials given in the book shown on the slide, they should include one or more of the following components: sensing elements, actuator system, and real-time information processing system. The ability of smart materials to fulfill actuation and sensing function is mainly utilized in condition monitoring of structures in the environment. At present, smart constructions show in the greatest prospect in the various fields: aviation and space, automotive industry and railway transport, medical application and precision tools, sport goods for new generation, appliances. Also, smart construction have proven themselves in the field of online structural health monitoring of concrete bridges and other civil structures in real time. At present, the greatest prospect for the embedment of required elements into intelligent systems associated with use of fiber-optical sensors and piezoelectric materials. Sensors which are based on the fiber optics can measure different physical and mechanical quantities. Also, fiber optic sensor can be easily integrated with other equipment for remote monitoring and allowed observing composite structure during all stages of its manufacturing, design, testing, and operation. One of the main tasks in using fiber optic strain sensors in the composite material is related to the strain measurement. The interrogator generates and transmits through the optical fiber the optical signal, which is wideband signal in the prescribed interval of wavelengths. This signal is partly reflected from the Bragg grating. With an external effect on the Bragg grating, strain or temperature, the Bragg wavelength is shifted. In the general case, relation expressing the relationship between the Bragg wavelength shift of the components of the strain tensor for the isothermic case are shown on the slide. A particular case is practically important when the optical fiber in the region of the Bragg grating is in a state close to an axial stress state. In this case, the relation between the axial components of the strain tensor are valid. To obtain information on the behavior of civil concrete engineering structure in the early stage of operation, an experimental stand was designed and created. On the slide, the photo of experimental stand is shown. The parameters of steel frame also shown on the slide. On the frame, two movable brackets are placed for the laser position sensor at the top and bottom level of the sample. Also, on the frame, the mounting beam for the fiber optic strain sensor line is placed. Laser position sensor with built-in microprocessor control system LS. The range of the displacement measurement for the sensor is 10 mm. Weight platform equipped with two sensor gauge strain sensor to control the sample weight. The strain gauges are assembled according to the Wheatstone full bridge scheme with thermal compensation on separate part sensor for mounting the sample temperature and sensor for mounting the temperature and humidity are also installed on. The sample is a concrete cylinder with parameters shown on the slide. A sample was made of concrete mix of strand class B15 in order to provide control over the process of its shrinkage for a long time was created. The duration of the experiment is defined as time required for the sample in the current temperature and humidity condition until the shrinkage is completely stopped. Shrinkage of the concrete sample takes place in 3 stages. The first stage is plastic or capillary shrinkage, which occurs as a result of evaporation of water from the concrete mixture before hardening begins. The second stage is autogenous shrinkage of concrete. It's associated with the direct hardening of the mixture and the further drying as a result of cement hydration and water evaporation during cement exothermy. The third stage is the shrinkage upon drying of the sample, associated with the removal of all remaining water, which did not enter the hydration reaction and was not evaporated at the stage of aftergenous shrinkage. Shrinkage during drying depends on humidity and ambient temperature, being reversible in contrast to capillary and autogenous. The purpose of the experimental study is to verify the ability of fiber-Bragg grating sensors to register strain changes in concrete at various stages of technological shrinkage. Registration of the process induces strains in the concrete sample obtained with the help of fiber-optic sensor based on the Bragg gratings during 4 months is present on the slide. During the 4 months data recorded for the sample described above, the following measures were carried out. Analysis of the results showed the following. Plastic or capillary shrinkage of the sample was realized at the first 3 hours of the experiment and was about 3.6 mm. The shrinkage graph at this stage can be seen in Figure 2. Its end corresponds to point 1 in Figure 2. This deformation of the sample occurs during the period of the most intense moisture evaporation from the concrete mix and lasts until the concrete mix sets or hardens. The end of this stage corresponds to a peak in humidity, which can be observed in Figure 3. The free surface of the sample at this stage begins to harden in water, which has not yet entered an exothermic reaction, and does not participate in the hydration of concrete mixture cases to evaporate. Last is confirmed by measurements performed by the humidity sensor in the experimental stands, which data begins to drop, while the temperature sensor data on the contrary rises. The second stage of shrinkage of the mixture begins. The autogenous shrinkage of the sample occurs as a result of hydration of the concrete mixture and the accompanying exothermy. This stage is shown in Figure 2 and corresponds to points 1 to 3 on the shrinkage graph. It should be noted that at the stage of capillary shrinkage, the fiber-Bragg grating sensor didn't show any significant change in the sample strength, which is understandable. Since the mixture was in the liquid state, the adhesion along the fiber-Bragg grating sensor was not enough to obtain the strains on the liquid concrete mixture. As can be seen from the graph in the Figure 2, adhesion along the fiber-Bragg grating sensor and the mixture begins to appear after the capillary shrinkage stage and was complete, at the stage of autogenous deformation. At this stage, the sample cases to give moisture to the air and begins to harden, as can be seen in Figure 3 and 4. As a result of adhesion, fiber-optic Bragg grating sensor begins to display part of the strain of the sample, which corresponds to points 1 and 2 at the same time in the process of cement hydration and sample exothermy. Both the sample and the surrounding space are heated. At this stage, the sample heats up itself and heats the environment in the experimental stand to a maximum temperature and begins to cool, which can be seen in the Figure 5. The expansion due to the heating and hardening of the cement gel and sample ends. The sample hardens and begins to gain strength, which is shown in Figure 2.3. Next, the sample is dried and the third stage of shrinkage of the concrete mixture, which is most noticeable according to the fiber-optic sensor data, because the shrinkage is small enough to be measured integrally on the sample. It should be noted that under the given condition of the sample drying and hardening in the tank, the mechanism of the reverse shrinkage of the sample at the most intense cement hydration reactive stage was revealed. This phenomenon of the shrinkage appearance with the opposite sign or sample elongation is caused by violation of the optimal water-cement ratio for concrete hardening based on the Portland cement. It should be underlined that the measurement stage, which correspond to point 2 and 3 in the Figure 2, it can be seen that the elongation of the sample was about 0.15 millimeters, which in terms of the strain was 0.3%. It's shown on the figure 6. The deformation of the sample is shown also on the figure 6, and it's colored in red line. The data were obtained by dividing the value of the reverse shrinkage, which correspond to 0.2 and 3 in figure 2, by the length of the sample itself. The fiber optic sensor data, which corresponds to the 0.2 and 3 in the figure 2, also showed a positive strain increment by an average value of about 0.3%. The main conclusion are shown on this slide. I would like just to add that the results were obtained when creating a concrete sample with embedded fiber optic strain sensor based on the Bragg gratings. With the help of the fiber optic sensor, the entire history of the process-induced strains was fixed and analyzed. The mechanism of the reverse shrinkage of the sample is revealed, and we can say that the study of the revealed mechanism in the future will allow to understand better the concrete hardening process based on the Portland cement and describe the dependence of its physical and mechanical properties at different stages on the composition of the concrete mix. Here I would like to show some perspectives of this study, and thank you for your attention. I will be happy to answer your questions.